Okay, so this morning I will be putting more emphasis on the erosional processes. So on the first day, we saw mostly the river processes, in particular river incision, because as I explained it, there are several reasons to consider that it's the river network is a driver of the erosion in the mountain landscape. But even if the river are the main driver, there are other processes, other important processes that permit to denude, erode the landscape on Earth, and in particular in mountains. So I will be presenting mostly Hillslope processes and also landslide among the different Hillslope processes, because in particular in high mountains, landslide is a quite important process. And if I have time, I will say a few words also on the glacier and glacier erosion. So I think in the next days you will have a presentation, but maybe more focused on just on ice flowing and not so much on the glacier erosion. So I don't know. So I will say a few words about that, and I will try to give you some kind of broad view, and at the end of each presentation of process, I will give a few examples on the Himalaya, in particular, trying to give you some insight about the rate of the erosion rate associated to the different processes in Himalaya. So I will be presenting very quickly the soil fabric, in particular the chemical weathering, then the different slope processes. So we already saw what's going on with the sediments when they arrive in the fluvial network, in particular the river erosion, then a little of glacier erosion. So all the equation we need to describe in general these erosional processes is first of all a law of conservation mass. Mass of element, mass of sediment, and also we'll need, in most cases, a law of transport of sediment, transport of solute material. So I will try to give you some general insight, not focusing very particularly, but providing some broad view and trying to give you the order and magnitude and the efficiency of the different Hillslope processes and glacier processes. And I will be speaking a little about the controlling factor, in particular slope and climate, what is most important for the different processes. And sometimes I will give you some example to show how the knowledge we have on the equation that govern the specific process can explain the final shape of the landscape. So again, this view, the mountain landscape governed by mostly free domain and different processes, glacier, Hillslope processes, and fluvial network. So there is one necessity for the erosion to occur and to get the sediment transported by the river. We need to transform the bedrock into material which has a smaller grain size, so it can be silt, sand, it can be also blocks, but we need to reduce the size of the material on the slope before being able to transport it. And the second thing, we need a transport process. So we can have just gravity, so it will be just a fall, and we can have also entrainment. So it can be entrainment by water, entrainment by ice, in case of glacier, or entrainment by the wind. So in the desertic part, you know that it's mostly by the wind, but in fact, I will not speak about desert part and in particular aeolian transport. So I will just focus on what's going on the Hillslope by gravity and due to water, whatever it is, water liquid or water solid like ice. So first, how do we produce the sediments on the Hillslope, or how do we reduce the size of the bedrock to some transportable size? We have two kinds of processes, physical weathering and chemical weathering. So physical weathering, it's mostly a loss of cohesion of the rock by different processes that can be mostly, when the most efficient one will be cryoclasty, so the action of frost and the action of ice expansion in the fracture that makes disintegrate the rocks. But in close to the sea, for example, we can have also the same effect with salt crystallization. So in that case, we speak about alloclasty. We can have some process linked to the denudation and the decompression during the denudation. In that case, we will speak about exfoliation by decompression. And obviously, we can have any kind of propagation of opening of fracture by biological elements like root development. So a few examples. So in that case, it's basaltic pipe. So it's already during the cooling of the lava flow, there are already fracture created. So it's just a matter of having rockfall by, from the joint which are being already created, also in sedimentary rock, but in other places, for example for granite, we'll get some disintegration either by thermoclasty or by cryoclasty, or in big granite like in the Sierra Nevada, we can have this kind of peeling or exfoliation of associated to the decompression. But good part of bedrock weathering, in particular when you get some vegetation cover, it's due to chemical weathering. So chemical weathering, it's not. It's a process that basically modify the chemistry and the mineralogy of rock, and doing that will affect also the structure and the cohesion of all the mass of the mineral within the rock. We can have different type of weathering or different type of reaction, dissolution, acid attack or acid hydrolysis by different type of acid, the one coming from the dissolution of CO2, so carbonic acid, but we can have also the acid from the vegetation, like humic acid or oxalic acid, and you can have also sulfuric acid. If you have pyrite and you oxidize the pyrite in your rock, then you get some sulfuric acid available for weathering your minerals. So according to the kind of environment and according also to the type of mineral in your rock, you will have different type of weathering. So obviously for gypsum or halite, you will have mostly reaction, chemical reaction of a type dissolution by water. In the case also of carbonate, again, dissolution, but by mostly acid. And you will have, for example, as I was mentioning, for pyrite, oxidation, same for pyroxene. For mica and feldspar, it will be mostly some acid, partial solution by acid attack, so the acid I was mentioning, and doing that, we will produce mostly clay mineral. So these different minerals have different type of reaction rate, and it will condition in some way the way that the different rock outcropping on Earth will be modified by chemical weathering. So if we go from quartz to calcite, you can see the rate compare or reference to the rate for the plagioclase for albite. So albite 1. So you can see the quartzite in some ways put in solution almost 50 times slower than feldspar. By contrast, for calcite and dolomite, then you have 6 orders of magnitude in terms of dissolution rate or dissolution efficiency compared to albite. So if you look, for example, this graph, I don't know if it's very readable, but you can see that outcropping on Earth, you have mostly shales and gypsum and rock salt. There are very few outcrop on Earth, but if you consider the efficiency of dissolution of gypsum or salt, you see that the contribution of a small outcrop will be very important in terms of solid load, and mostly the most important contribution to solute load, so to elements in solution in river water, it will be from carbonaceous rocks, from carbonates, calcitic and dolomitic limestone. Another way to look at this graph is to compare the rate of dissolution of calcite, dolomite compared to quartz, completely dwarfed in terms. So we already understand that different type of rock will not react the same way to dissolution and to weathering on Earth. So once you get water arriving at Earth's surface with vegetation action, you begin this process of weathering, physical weathering and mostly chemical weathering, and it's produced by percolation of element, this partial dissolution, disaggregation, and you begin to see that your bedrock is converting in smaller elements. And as we can see, for example, at the limit between the bedrock and the soil in this granitic environment. So soil fabric is a matter of pedology, so I will not give you more insight on this issue, but pedology science has a whole bunch of description of soil and soil evolution. Then below the soil, we can find for example, in granitic environment or in a metamorphic environment, we find first some level of saprolite, and below that saprock. So the saprolite or alterite is some kind of deeply weathered bedrock in which mostly the feldspar, in the case of granite, mostly the feldspar and the biotite have been turned to clay. And because all the mineral that make the skeleton of the rock has been dissolved, you still have the structure of the wall rock. So if you have, for example, a dike or a silt, you will still see the dike or the silt. But if you take a sample of the rock, then it's completely clayey, and you can crush it in your hand without trouble. So below the saprolite, you get some kind of saprock, so it's partially weathered, and if you take in your hand, you can still crush it, but instead of getting a lot of clay, you will have more like many chips in your hand. So the weathering is helped by, because it's oxidation reaction or acid attack, it is governed by the availability of oxygen and availability of water. So obviously, the place where you will have more water and oxygen, it's arriving on your rock, it's along the fracture, through the fracture permeability. And we can see, for example, here, this fracture, and here a small thin section in a rock partially weathered, and you see the fracture which has already filled in blue by some clayey material. So most of the reaction are occurring first in the fracture, and then slowly and slowly they propagate through new fracture into the unweathered rock. Same at medium scale. If you look, for example, at granite, which is already fractured, so let's say either by thermal effect or due to decompression or some tectonics issue. So you have the fracture, the water circulating in this fracture, and the weathering will be propagated from the fracture toward the center of the blocks. So finally you will get some coarse, what we call some coarse stone, which partially weathered granite, and here all around you will get some more weathered material along the fracture. So another view of probably a set of fracture like that, the weathering propagating from the fracture toward the core stone, and you isolate in that way some less weathered hurt of your rock. And if by some climatic event you strip the vegetation and you clear all the thin material, you can end up with this kind of cow of blocks with big ball of granite, so erosion in ball, we call that in French. So as I said just before, two essential ingredients, water and oxygen. And we get a sense of this importance here by looking at this diagram I've shown you 2 days ago. So again, it was yesterday, sorry. So soil production rate measured by barium-10 compared to the soil depth. So you see that, and it's different places in Australia and California, you see we observe more or less the same. So when the soil thickness is large, then the soil conversion rate, so in some way the rate at which the bedrock will be weathered and transformed into soil. So this rate is much lower. It's just because the thicker is the soil, so the more difficult for the water and mostly for the oxygen to reach the bottom of the soil and the bedrock. So for that reason, the rate of soil production will be decreased if you have a fixed soil cover. During bedrock conversion into soil, we saw different factors. First of all, the type of rock and the type of mineral. But we have also, because we have acid dissolution, we have the role of the pH, so which is governed partially by the vegetation and the root activity. Obviously, if you have some weathering, there is a specific role of the surface of contact. If you have large surface of contact between the rock and the fluid, then you will get more weathering. So for that reason, people have been considering that chemical weathering is in some way related to erosion or physical erosion for the following reason. If you get large physical erosion, then you bring a lot of material at the surface. So first, maybe you will have the chance to strip regularly the soil, so to get a thinner soil cover than in a slow eroding environment. And second, by bringing fresh material towards the surface, you will bring a lot of new specific surface of contact between the fluid and the rock. So you will increase in some ways the chemical weathering. So more physical erosion go to more chemical weathering. But it seems that in the measurement, in particular the one made by West and his co-author, that there is some kind of effect of saturation. So for denudation rate larger than, let's say, 1 or a few millimeters per year, instead of keeping on the same relation, increasing relation, then there is some kind of saturation. And it has been explained by the fact that maybe at some stage we are limited, or the chemical reaction are limited by the kinetic of the weathering reaction. So there is a competition between the rate at which you are bringing fresh material to the surface and the rate at which you can dissolve it. So if it's carbonate, it's not a problem. We saw that we have a huge capacity of the system to weather dolomite or calcite. But if you have more like granitic or metamorphic environment with plagioclase or quartz or mica, then we saw that the weathering rate or the dissolution rate is not so high, so you have some kind of kinetic limitation. You cannot weather as fast as you would. In any kind of chemical reaction, there is also a role of temperature, at least on the kinetic of the reaction. So we would expect to have a more efficient weathering because of more efficient, more rapid reaction kinetic. We would expect an increase of weathering with temperature. So it's more or less what we can observe, in particular, if you look at the equatorial part, you get in general more weathering due to this higher temperature and the combination also with higher precipitation or high precipitation, because you need, if you have heat, or temperature, high temperature, you can have rapid reaction, but if you don't have water to make the dissolution effect or the weathering, then the weathering will be staying low. So you can see that on this kind of graph where people have been plotting different value corresponding to different basaltic islands. So Rainian, basaltic environment, Rainian volcano, San Miguel volcano, Icelandic volcano, so different runoff value. And you see that on average, the more you have runoff, the more precipitation, more runoff, the higher is your weathering at the scale of your basin. And here, the total dissolved load as a function of temperature. So again, we see for basaltic rock a progressive increase of the dissolution of your basalt by the increase of temperature. So we have this double role or positive role of temperature and precipitation. And the combination of two can give you this very schematic and qualitative view on where you can get a large weathering action. It's in the tropic area because you have moisture availability, so precipitation, and you have also high temperature. In contrast, in northern latitude or southern latitude, close to the pole, you may have high precipitation or sufficient moisture, but the temperature is much lower, so we expect lower weathering rate. So depending, I will skip that part. So the effect of temperature and precipitation makes that you can have different kind of action, dissolution, acid dissolution, and different soil type because of the different weathering and also because of the difference of vegetation. So typically in Arctic weathering profile, you will have a mix of physical and chemical weathering leading to active disintegration, in particular by cryoclasticity of your rock. In contrast, in the tropic, the chemical weathering is dominant, and in that case, you will end up, for example, with a red weathering profile and large soil development. In terms of rates, we can see at these different studies. So this one, was to look at small basin, looking at the solute content in the water coming from the small basin. So we can estimate the export of material in the water, the solute content in the water, and this gives an estimate in ton per square kilometer per year, and convert in erosion rate. We have value here that goes from a weathering rate or chemical weathering rate between 0.01 millimeter per year to 0.1 millimeter per year. If we look again at this rate of soil conversion, obtained this time with barium-10, we are in between 0.01 millimeter per year and 0.1 millimeter per year. So same range of value. And here also, chemical weathering rate, it's probably measured by solute content also in water, and similar rate. So this time we go from 0.001 millimeter per year to 0.1 millimeter per year. So similar rate. And to end up with what I was saying about the role of precipitation and temperature on weathering. So I will just mention this other study, but I've tried to document the role of precipitation. And in fact, in several areas on Earth, the link between weathering and precipitation is not so obvious. So for example, in this first study in California by Reeve and co-author, they saw that looking at different places, going from desertic place to a much wetter place where you get almost 2 meters of precipitation per year, then the erosion rate, and we can estimate in this low environment, its good part is due to chemical weathering, then there is almost no difference between the desertic environment or the dry environment and the wet environment. So the relationship with precipitation at the scale of this basin is not so obvious. And same thing in this study by Cartier and co-author. They look at the barium-10 and also suspended load in small river coming from the Andes along the Chile coast. So I'm not sure, I don't know if you are familiar with South America. So you have on the western facade of South America, you have the Chile country, and the northern part of the country is really dry. Central part with the capital Santiago is semi-arid or to middle dry, and then you go to wetter climate toward the south, and you can see that the erosion rate in that area is around 0.1 millimeter. We go toward an increase of the erosion rate when we go from very dry to semi-arid, and then when we go from semi-arid to wetter climate, then again we have a decrease of the erosion rate. So it seems that maybe there is some tectonic issue, but it seems also that here there is a non-linear response of the erosion rate and probably of the chemical weathering to the increasing rainfall, with first an increase and then maybe a decrease due to the role, for example, of the soil cover and the role of vegetation, because the vegetation will protect the soil from weathering and also from erosion or physical erosion. So the product of chemical weathering will be, first of all, ions that goes into solution in the water. Then, because of the disintegration, you'll get a cover of debris and fragment of extended granulometry. So we saw that we can have coarse stone in granite environment that are several meters, and we can go also towards sand, silt, and obviously clay. And this extended granulometry is mostly due, or it's increased when the weathering is non-uniform or heterogeneous, because you will have more weathered rock and more clay content close to the fracture, and more large glass in between the fracture. So what about the Himalaya? So I don't have so much, I didn't compile a large bunch of data from the Himalaya, so I will just give you a small insight from a study we have done in the past. So in central Himalaya, along the southern face of the Himalaya, there is a small basin called the Kudi Basin, which is 136 square kilometers. So I will present later other example of this small watershed. So I give you the characteristic. So it's draining mostly the gneisses of the high Himalayan, but in its lower part it's draining also the lesser Himalayan metamorphic units. And it is affected by intense rainfall, like 4 meters of precipitation during monsoon. And for that reason, you get dense vegetation and also relatively thick soil. So I have a picture here. So some soil along the crest can be more than 2 meters deep. So a soil with a large organic content. So here, this is the total organic content in the ground. So at close to the surface, you can have up to 5%, up to 10% of organic content. And then down to 1 meter, then this total organic content will drop. But still, you have weathered bedrock with a thick saprolite and saprock that can go down to 10 meters. So even if we have quite efficient physical erosion in that area, because of the dense vegetation and the high precipitation and relatively elevated temperature, then the weathering, the chemical weathering and the soil conversion is quite efficient. So we have a small view here of this dissolution effect. So in the red line, the red and green line will be the initial signature of the bedrock, underlying bedrock. So in terms of, here it's potassium over aluminium, sodium over aluminium, and calcium over aluminium. And here it's hydration of the silicate. So why do we normalize by aluminium? It's because aluminium is considered as immobile element. So we are looking at mobile elements. So the potassium is mostly in the car feldspar and in the mica, and the sodium is mostly in the plagioclase. And if you get, for example, dissolution of a plagioclase, then the sodium will go into solution in the water, and the aluminium will stay in the secondary phase, in the clay in particular. So here we get the concentration in potassium, sodium, and calcium of different Himalayan soil in all that area, and you see that they are systematically and over 3, even 5 meters depleted in mobile element. So some weathering down deep, several meters, and this weathering is characterized also by the hydration of the silicate. Obviously, if you create clay minerals, they will be more hydrated than the initial mineral, whatever it's feldspar or mica. In terms of rate, I've shown this slide yesterday, so I'm not interested in that part today. I'm mostly interested by the measurement of Berrien 10 along the crest of this basin. So it gives you some idea of the erosion, and if it's at steady state, maybe if it's mostly evolution by soil conversion, it gives you an idea of the soil conversion rate. And again, the value are in between 0.01 to 0.1 millimeter per year. So soil production rate in Himalaya, they are not very different from what what people have documented in other places on the world, whatever they are in tropical island or in a little more northern countries. So a few conclusions. To get weathering, you need water and you need oxygen. That's the important aspects. So you need to be in contact permanently with these two elements to get efficient chemical reaction. This weathering is important on the Hillslope, obviously, to get decohesion of the material and to get granular, some kind of granular type material easy to be transported. And obviously, if you have already, by tectonic aspects, some pre-existing fracture, that will facilitate the deep weathering because you make possible the circulation of water, bringing oxygen, water, and acid downward into the fracture and into the bedrock. In terms of controlling factor, climate has some kind of important, is an important driver of a controlling factor of weathering. We saw it's maybe not always as straightforward because I show you two studies where it seems that people seem to observe some kind of nonlinear effect between a nonlinear relation between precipitation and slow erosion rate, so probably a soil conversion rate. But anyway, we expect some kind of positive role of water for the explanation I gave you previously, and a positive role of temperature. So let's move to more physical erosion of the Hillslope. So, yeah. You say 15? The rate, it's meter per million year. So it's here, it corresponds to 0.01 millimeter per year, and here, 0.1 millimeter per year. because if you are your mineral like that, so you bring it towards the surface by erosion, and if you bring it slow enough, then you have time to dissolve it. But if you bring it very quickly, because it takes time to dissolve because of the kinetic of the reaction of the acid dissolution, then when your mineral arrives to the surface, ready to leave by erosion, then it is unweathered.
So it means if a place is denuding if a place is denuding very fast,
yeah,
then the chemical weathering of that place will be less.
Less because you have no time to weather.
Okay, acha.
So it's there is a competition between if it's very slow denudation, then you have this thick soil cover and thick all that material is already weathered, and the fresh rock that can be weathered is too deep. So when the water is arriving here, it has lost already some kind of some part of its acid, and there is it has lost also part of the oxygen. So the capacity of the water arriving here, it's much less aggressive than in this kind of when the physical erosion is higher and the soil cover is lower. So there is a competition between the effect to be close enough to the surface to bring to have some aggressive water, but if you go to the surface too quickly, then even if you have aggressive water, there is not enough time because you need some time to do the chemical dissolution. You have not enough time to really dissolve your mineral. So when it arrives at the surface, it is still fresh and flushed away by surface erosional process. So finally, you arrive at this when you arrive here, the most important in the competition between kinetic reaction and bringing fresh material, when you arrive here, the kinetic or the speed of the weathering reaction is the most important or the controlling factor, and this explains this decrease.
Yeah. So suppose if a place is denuding very fast, the source area is denuding very fast, so it means a lot of sediments are coming. So I collect a sample in the downstream.
Yeah.
In the source, from downstream information, I found that denudation in the source is very high.
Yeah.
So it means a lot of sediments are coming from there. So now I know that in that place, since denudation is very high, so their chemical weathering is very less. Can we reach that conclusion in that source? Because you said that when denudation will be very high, then the chemical weathering in that place will be low. Then the question will be, in the source, what is the process the sediments is forming? Then what will be the answer?
Whatever it is, I mean, if you have So if you are considering the source here, I'm not sure to understand your question, but the process will be, the Hillslope process will be the same here and acting on the Hillslope. So you have first soil conversion and at the same time physical erosion, so either by a pellicular physical erosion or it can be also a landslide or deep erosional process. So the material, when it's brought to the surface, begin to be weathered, and you are exporting whatever you are here or close to the source, you are exporting material which is partially weathered. In particular, if you have landslide, you will bring to the system elements which are unweathered from the deepest part, and more material coming from the soil which are more deeply weathered. So you have a mix of sediments, blocks, for example, which are unweathered, and material which is weathered, mostly silt and clay. So I'm not sure to understand what is your concern about the source.
So I think so in that source, I think we can say that. But can we say that that source is having no chemical weathering, but it is having a lot of physical weathering?
No, physical erosion.
Physical erosion.
Yeah.
So if this is so, can we say that that source is a place where a lot of landslide activities are going on? Because this is the only explanation that we can reach if there's no chemical weathering, but the only physical weathering is the active in the source. It is so?
Yeah, we can say so. That the higher the erosion rate is by landslide, the higher the proportion of fresh material is arriving in your fluvial system. So normally you would expect to have the ratio between physical erosion and chemical erosion to be much more in favor of physical erosion. So to give you an idea, and we can get an idea from the number I gave you, so the soil conversion, so in some way it's a window on the chemical erosion. It's on the order of, let's say, 0.1, between 0.01 and 0.1 millimeter per year. So if you erode the landscape at a rate of 1 millimeter per year, so it means that the chemical erosion will represent between 1 and 10% of the total denudation. So it means that physical erosion is 99 to 90% of your the total denudation.
I think I have. Can you move the next slides? Okay. So here, just at 70-degree latitude, we can say that the regolith formation is less compared to the 0-degree latitude. So there it is because of what is the reason here? Why it is less here and why it is more in 0 degree?
So it's a very schematic view, and it's well, here I didn't explain it, but this. Right, maybe it's the battery is dying. Anyway, so it's a model where people, where Godoris and Kofer have put the precipitation and temperature map, or the climatic map, and they introduce also all the possible chemical reaction acting during chemical weathering with some model of the soil evolution. So they include also the relation between soil thickness and the rate at which chemical weathering and soil production is done. And they obtain this kind of map. So you can see on this map, which is a result of the model, that the highest weathering rate or silicate weathering rate are obtained in the tropic here, and also in that part, so in the zone of the southeastern Asia. And the three common factor in Amazonia, Central Africa, and here, it's the temperature, but also mostly the precipitation. So all around the monsoon area, whether it's Indian monsoon or southeastern monsoon, southeastern Asian monsoon, then you will get temperature, high precipitation, so you will get higher rate. Here in Sahara Desert, no precipitation. So no precipitation, so no weathering. It is the same in this schematic view. In the tropics, you have both water available for dissolution and also temperature or high temperature that favor the speed of the reaction. So you have efficient weathering. When you arrive in that part, you have warm temperature, but no precipitation because you are in the desertic belt around the tropics lines, and then no, the chemical weathering will be limited by the lack of precipitation, the lack of water, so there is much less soil production, so very thin soil. When you arrive in the northern, in the high latitude, between 50 and 70 degrees, then you get, again, available precipitation. Usually, for example, in Europe, average rate is between 500 and 1,000 millimeter of precipitation per year. So if you have water, but temperature are less. So in fact, weathering rate are less efficient, and soil, for that reason, are less developed. And when you arrive at very high latitude, it's permanently frozen. So first, the biology is down to zero because it's always frozen. And also, there is almost no circulation of water because the water is frozen. So for that reason, you will expect a little of physical weathering by cryoclasty, but almost no chemical weathering.
Okay.
So the limiting factor in that case, it's mostly temperature.
Thank you.
Excuse me, Jérôme.
Yeah.
That's a very nice talk, a very nice insight on chemical weathering. So actually, I would like to little bit clarify what Viraj was asking is what will be the chemical weathering rate in the upstream and downstream region. Basically, what he's saying that if it is more physical weathering, then what about the chemical weathering? So basically, like you have also mentioned, that it depends on the rainfall and temperature condition as well, because it is a chemical reaction. So if in upstream region, if more physical weathering is going on, then more number of mineral surfaces are exposed. And if the rainfall and temperature condition are prominent, then you will get a signature of high chemical weathering rates in the upstream region as well. Like in my regions, I am getting a few of the water sets that in upstream region also we have a high chemical weathering rates also. So there is not like if you are getting a more physical weathering then less chemical weathering. In fact, people have reported that physical weathering basically induce more chemical weathering. So it's like that, and certainly it depends, like rainfall and temperature condition, like you have, like Jérôme has also shown the map of throughout the latitude how the temperature and rainfall conditions are changing, and likewise the chemical weathering also depends on those conditions. So my question is basically, Jérôme, that I am looking for the weathering rates based on the dissolved load signature, which is transported by the rivers of an area. So the problem that we are finding that different minerals have different intensity of weathering, and we cannot say that mineral are congruent weathering signatures. All minerals, like mainly silicates, they are incongruently weathering, part in the incongruent weathering. Like carbonates and salts, they go into dissolution.
Yeah.
But like for silicates, basically they have a range of silicates. Like in Bowen reaction series, we find that the late crystallization have a more resistance to chemical weathering, and the early crystallization have high uh, rate to susceptibility towards weathering. So uh, basically, how we can define the chemical weathering reaction based on the chemistry of this transported material, dissolved load or suspended material or bed rock material. This is one of the challenging part to define a weathering reaction of an area. So, what is your insight on this?
Unfortunately, I'm not geochemist, so I can hardly answer your questions. Well, yeah, maybe, well, first, a small precision. Yeah, you're right that in the Himalaya, we have high chemical weathering rate. The red line is some kind of model. So we are not sure that we observe really this decrease. This is due to the model. If you just look at the data, it's more like a kind of saturation. So the higher the physical erosion, in any way, the higher will be the chemical weathering with some chemical effect, with maybe some saturation. But in terms of ratio, when I was speaking about the 99% of physical erosion, so when you do the ratio of physical erosion over chemical erosion, because of this saturation effect, then from here to here, this ratio will be increased permanently in terms of the ratio between physical erosion and chemical erosion will be strongly increasing from here to here. So, to go back to your questions, in the Himalaya, if you look at, for example, the solute in the water, the dominant ion is calcium, and it's coming from, as you said, the easiest rock to dissolve is carbonate, and all the Tethys series and also part of some units in the lesser Himalayan are made of carbonate. And good part of the dissolution in the Himalaya is due primarily by dissolution of carbonate. And then you have also a lot of silicated rocks, and you have also some dissolution of silicate material, so we can see it in the depletion in the soil, by depletion in terms of sodium and potassium. And what was your exact question about the silicate?
I was concerned about the mineral weathering reactions, basically. I was more concerned about the mineral weathering reactions.
I'm sorry.
It's weathering reaction, na? It's a reaction. So basically, the different area have different kind of weathering reactions. So that was my question: that how we proceed to this defining the weathering reactions.
Oh. Again, I'm not geochemist, so I never practiced myself, so I can hardly tell you about the strategy and what can we do in such or such environment. But the classical, well, as far I understand, this classical way to look at weathering, it's either to look at water and to make a budget of the solute and the flux of the solute over the year, average flux of solute. And the other possibility is, and I will show you probably later, it's to look at the sediment, the chemical signature of the sediments downstream, and to compare to the signature of the initial bedrock. And if there is some misfit, if, for example, less sodium in the sediment than in the bedrock, then by making some mass budget, you can also calculate the flux or the quantity of sodium that has been dissolved. So in the case of the Himalaya, this kind of exercise has been done by colleagues in the downstream part of the system, for example, in the Ganga River and the Brahmaputra River. And the Ganga River, I don't remember, but for several elements, the budget, when you compare one method, so that measuring directly the solute in the water, and another method measuring the difference between the chemical composition and the sediment of the bedrock, for most of the elements, you get some close match, but for one or two elements, it doesn't work so well, so there are still some question about what's going on and what are the units that are measuring most or not. So it's what I can tell you. Yeah? Yeah. Well, it's a very rapid consideration. It's where is it? So the rate, this one, it's California, Australia, semi-arid environment. This one, they are basaltic rocks, some of them from relatively wet environment. La Réunion Island, it's high relief. So you see that we have a value of 0.1. And here, it's the soil conversion rate. It's on the crest. In fact, those authors, so I think it's Arjun Aimzas, I'm not sure he made some measurement on the Hillslope affected by colluvium and so. So this rate I was giving, it's mostly for the crest. So in that case, the roller slope is not so important. So whatever is the relief or not, here you are looking some more flat area, and slowly evolving by bedrock conversion. And the rate they found, it's more or less the same range as the one we can find in California, hilly, semi-arid environment, or even in La Réunion Island, which is more deeply eroded region with intense rainfall. So again, I'm not specialist of soil production, so I don't know all the literature on the subject. So I will show you just a few examples later on, where in terms of soil conversion rate and some limiting effect of soil conversion rate, there are two recent studies, one in the San Gabriel Mountains in California and the other one in New Zealand, where people have proposed that locally we can find much higher soil conversion rate, up to several millimeter per year. But to my knowledge, there are only 2 studies that document such a high rate, and in most studies, soil conversion rate are below 0.1 millimeter per year. And it seems that Himalaya doesn't make exception.